All right. Well, thank you. Being the last speaker, I decided that, well, my talk should be light on the technical details. I'm sure it's been a long day, and you must be exhausted. Well, when I was removing technical details, I realized I removed a lot of parallelization issues as well. But, well, it's still about handling extremely large graphs, so there should be something interesting for you. All right. So I'll be talking about, I'm not telling you anything, something you haven't heard before today, but today I'll be talking about sampling and streaming style algorithms. And by these, well, these algorithms, what they do is they look at only small portion of your graph. You have a metric in mind, and I want to compute this metric by looking at only a small portion of your graph. And I'll give you an estimate, and on top of this, I'll also give you an upper bound and lower bound. So I'm 99% confident that the error is, well, number is 0.5 plus minus 0.01. So that's the kind of algorithms we're trying to design. And by doing this, well, you can compute general trends in your graph. So if something is very frequent, you can count it. But you cannot, or something is really big, you can detect it. But if you're looking for a needle in a haystack, well, you cannot do sampling or streaming algorithms. And I'm not sampling, well, it's not an alternative to parallelization. Actually, they get along well with each other because, well, if you're doing something efficiently, well, you're communicating efficiently as well, so it performs well. Well, they get along well unless you're trying to cut flops or something like that and trying to compute, well, report giant flop numbers. So this is, in terms of productivity, parallelization and sampling go well with each other. So what I'll focus on for these patterns is, well, graphs, and I'll focus on counting triangles in graphs. And what I care about graphs, well, if you look at the literature, there are only 2 references to counting graphs today. And it is an important problem, and people have used it in different ways. And when I talk about graphs, I'll talk about triangles and wedges. A wedge is, I have 2 friends, for instance. I form a wedge. Me and my 2 friends form a wedge. And triangle, if my friends know each other, I form a close to that wedge, and that forms a triangle. And people use these metrics for different purposes. Again, but it's all mostly friends of how often friends of friends become friends themselves. And the reason we got into this is we were trying to build a model, graph model. Well, we want to generate graphs. You'll give me a few parameters. I'll give you a graph, just like the real graph. And we were trying to figure how to do this. And something we observed in most of the real graphs was this clustering coefficients. And what you see in these plots is I'm not only looking at these how often friends of friends become friends, but I only divide it by degrees of vertices. Let's look at all the degrees of degree 5. How often they're trying wedges close. And it's the plot you see here. And they always start with extremely high. Well, for these co-authorship graphs, they start at around 1. For other graphs, they don't start at 1, but they start at 0.4. But they always start with very high, and then they decrease slowly. And you cannot, this is not something you can explain by the degree distribution. So you look at the same figures for Chang-Lu graphs. So this is a distinguishing factor, and I want to model graphs with it, so I want to compute these things efficiently. And that's how I get into this. So a little bit more of the definitions. So when I talk about, I'll say clustering coefficient and transitivity. Well, they mean the same thing to me. And we're talking about the number of closed wedges, the ratio of number of closed wedges to total number of wedges. Again, how often friends of friends become friends. And if you look at another way to look at this is it's 3 times the number of triangles because each triangle has 3 closed wedges. And so if you want to compute this thing by, all right, so this is an open wedge, you see there EFG because E and G are not closed. There's not an H from E and G. And here you see a closed wedge. And if you want to compute this by using enumeration, well, you look at all the wedges, right? You look at how often they're closed. And what we propose is, well, this was a core idea. Hey, if there's something, it repeats so many times, I don't need to look at each one. I'll just sample it. And I'll get a good idea about the ratio, how often this thing is closed. All right, so let's conceptually, let's make an index of all the wedges in the graph. So we don't need to, this is not an algorithm, so we don't do it explicitly. I can generate LKF. It's open. I'm also putting a mark next to each other. The next one is open, and this one is closed. And I'll keep doing this. And so let's define a number. So I have this index now for all the wedges in the graph, and some are marked as closed, some are marked as open. And let's define an experiment now. So I flip a coin. I'll choose one of these wedges, and I'll get 1 if it's closed, and I get 0 if it's not. So this is a random variable, and its expectation of x is exactly the 3 times, it's the transitivity. How often these things are closed. The wedges are closed. So if I know that, I can design an algorithm based on this. So instead of looking at one, I can keep repeating, pick another one randomly, and see if this thing is converging. The critical thing is, well, for a randomized algorithm, matching the expectation, that's the least you can do. Well, that's if your expected value is not matching the true value, you're in deep trouble anyway. What makes it a randomized algorithm better is, well, its concentration. If I run this experiment, if you can give me a bound on, trust me, this is close enough. So you have to provide confidence bounds. And how many samples do I need to get confident? Well, if you look at the Chernoff-Hafting bounds, it tells you exactly how many you need. And this is, in this figure, epsilon is the error, how much error I can tolerate. Clustering coefficient, let's say, I don't want to be off more than 0.01. You specify that. And delta that's my confidence. With my confidence 1 minus delta, let's say, I'm 99% confident that your error is less than this. So you only specify how much error you can tolerate and what confidence you want. And confidence usually comes easy. It's a logarithmic term. And then I can tell you how many samples you need. For instance, if you want the error to be less than 1% and you want to be extremely confident, you only need 38,000 samples. The best part of this is, well, what is not in this figure, and there's nothing specific about the graph, about the size of the graph. You can, well, give me a graph with 1 million vertices or 1 million edges. I'll need 38,000 samples. Make it instead of 1 million, make it 1 billion, I'll still need the same number of samples. So that's the number at the time to sample average increases, but the number of samples you need that does not. So that's the best part of it. And also when I present this, people get stuck on, how do you generate all the wedges? If you generate all the wedges, you already killed yourself. So you don't have to do that. So when you're sampling the wedges, you can do it in the air during the algorithm. So you know how many wedges each vertex generates. That's its degree choose 2. And I can pick one vertex randomly based on its degree. And then I choose 2 of its neighbors randomly, and that gives me a wedge. And this is the algorithm. And we implement this algorithm. So there's a lot of graphs, mostly from the SNAP data set. And you see the error, well, the true number, the exact number minus, absolute value of the difference between what's estimated and what's the true number is. It's always accurate. And this is you're seeing the speed ups here or over full enumeration that's extremely fast because, well, we don't do much work. We just use a fixed number of samples. And at the first slide, I was talking about clustering coefficients by degree. So you can compute those things as well. And you can compute other final level statistics on the same data. And I'll not get into that, but, well, this thing works in practice as well. And at the same time, I give you theoretical guarantees about, well, given the number of samples, how much the error can be. All right, so far, well, the algorithm is good. But what I was assuming that, well, conveniently, the whole graph fits into the memory so I can sample things and I can see if these things are closed or not. So what do I do for larger graphs? And so these are a few of the graphs. So I'm presenting the number of vertices, edges, wedges, and triangles on the logarithmic scale. So it does not fit into any single computer. And how do I predict the number of, or compute the statistics for these much larger graphs? Well, we had a Hadoop implementation. And the implementation is not really it's not explaining anything specific to Hadoop, but we implemented on Hadoop because we had data sets. Well, data is already on the Hadoop, and we had to implement it. And you can take the same ideas and use any other parallelization tool. You can use the MPI or GraphLab, which Joe was talking about today. And the same principles of the algorithm, well, fine-tuning will be different, but same principles of the algorithm will apply. So the key to success is that, well, if I'm doing sampling, I do if I do work efficiently, I'm doing communication efficiently as well. I'm doing very little work. And so this is the experimental setting, and we implemented the algorithm. I will just, at this part, I'm waving my hands. I promise you not to give too much of the technical detail. But, well, you can find the paper on arXiv, or if you can, if you're really interested, you can ask me how we implemented this. And this is, well, we are looking at computing the clustering coefficients by degree for the plots. And we use logarithmic means, 2,000 samples per bin. And you see the run times here. And as the graph gets larger, well, you get much more benefit for larger graphs. So different colors correspond to different phases of the algorithm. The big one, the first phase, is computing the degree distribution. You're computing the degree of each vertex, and that's what takes most of the time. So, and on the higher upper side, you see a plot for runtimes versus the number of edges in the graph. Well, we use edges because degree distribution, computing degree distribution takes most of the time. I wouldn't put too much weight on the exact numbers, but generally this scaling is linear. All right, so this was the second part of the talk. And I started with, well, how to do triadic measures efficiently on a single processor. And now if I have the data is too big to put on a single processor, I didn't explain you how we did it, but it's doable by using distributed resources. And the next thing is, what if I have the data streaming? And this is for many of the applications we are interested in. Data keeps flowing. So it's not like you want to store the whole data to disk first, pre-process the data later to make a simple graph out of it, and then you run your favorite algorithms. So we don't have time for that. The data keeps coming, and in real time or near real time, you want to be able to compute some statistics about your data. And think about the cyber security. The data communications keep coming, and when you do the analysis, it may be already too late. So for situational awareness, I want to do these things in real time. And so that's the next step for this talk. And, well, you can use streaming algorithms, a technique to, well, analyze data in real time, or you can use the same techniques to analyze data with using small memory, even if you don't, real time is not an issue. So when I say streaming, the model I have in mind is the data keeps coming, and each step, I have a new data item. And I'm the monitor there. So along with me, I have a small storage. I cannot store terabytes of data on the storage. Each time, I'm keeping some local data structures. For each data item, I do whatever I want. I update my data structures. I can update my predictions. But when I'm done with this data, it's gone. So I cannot go back and take a look at the same data again. So I'm making a single pass. And I want to process, do the updates, all the updates in real time. And again, well, it's the same thing with streaming. You cannot solve all the problems doing this, but there are problems you can solve. All right, so Beulah applied the same idea as wedge sampling, but it's a much harder problem now. So one of the components, well, the algorithm maintains 3 data structures. One is the edge reservoir. The second one is the wedge reservoir. And third one is a binary array. It keeps track of if the wedges are closed or not. The way the algorithm works is I maintain a random set of edges. And think about the graph formed by those random set of edges. It's sufficiently large. What is sufficient? I'm not telling you now yet. So these edges form wedges. So it's a graph. So eventually, some of the two of the edges will be adjacent to the same vertex, and it will form a wedge. And then that wedge graduates and gets to the next step. Well, I put it on the wedge reservoir. Again, I'll have a lot of wedges. I'll maintain a random sample of the wedges. I cannot keep track of all the wedges because there are billions of wedges anyway. And the next step is I put it on a reservoir. And then for each edge coming, does it close any of the wedges? So I check that. And if any of the wedges are closed, I put a 1. If it's not closed, I put a 0. And in the end, so there is still a problem. For compute the clustering coefficient, I compute 3 times the ratio of closed wedges. So the multiplication by 3, that's the unbiasing factor. I'll come back to that. And so it's just a lot of hand waving, but well, I want the edge reservoir to be big enough, but how big is big enough? So here, the birthday paradox comes to the rescue. What it says is actually a wedge is two edges having the same birthday. So these edges have two birthdays, but well, never mind. That's the details. Let's not get fixed on that. So if two edges collide by one vortex, they will form a wedge. And birthday paradox, what it tells me is, if I choose square root of n edges with extremely high probability, I will form a wedge. So I only need, so that gives me guidance on how big the edge reservoir would be. And if I want even more, well, multiply that size by k. If my wedge reservoir is k times bigger, I'll generate k squared more wedges. So put one, you get two back. So it's well, k squared of payback. So this is good. So I can design two algorithms based on that. Again, everything is based on birthday paradox. Whenever we're in trouble, we get back to the birthday paradox and use something to quantify things. The idealized algorithm is, for each wedge, I have an individualized, it's personal wedge edge reservoir, and all of them are size of square root of n, and I form a wedge, and I check if it's closed or not. So that's the idealized algorithm, and we can prove theorems. Well, we can prove concentration bounds on these things, so that's all good. But it needs a lot of storage. Each wedge needs this whole storage. What we do is, let's increase the size of this edge reservoir a little bit, and then we'll generate a lot of wedges. So that's what we do. The downside is, now my samples for wedges are correlated, because they're coming from the same sampled edge set. But in practice, we generate so many wedges that whatever fits into that wedge reservoir is only very small, and practically these are not, we don't see any problems in practice. Again, so this is how you start with theory, and then you engineer your theory to get a practical algorithm. And it was very effective in practice. And here are my numbers. Wow, I'm going much faster than I thought. All right, so there's one more thing I need to explain. So I said, well, I want to multiply the ratio of closed wedges by 3. And why did I do that? If I was doing wedge sampling, the initial version, so let's think about the triangle at the top. I have edges 1, 2, 3, and they come in that order, 1, and then 2, and then 3. And if I'm doing wedge sampling, pick any of those wedges, and I can see that, well, I can detect that edge, that wedge to be closed. But if I'm doing streaming, let's say I pick 1 and 2. I pick 1 and 2, and I'm looking for the edge 3. When it comes, I'll mark it as closed. Yes, I can detect that. But if I pick 1 and 3, all right, so I'm waiting for 2, but 2 is already gone. It's in the past. So I will not be able, even though it's closed, I'll not be able to detect it. And it's the same thing about 2 and 3. So for each triangle, we can unbias this, because for each triangle, there'll be only one wedge. That's future closed. That's closed by an edge that will arrive later. So the probability that I will pick that wedge among the 3 wedges is 1/3. And that's why I multiply the closest in the ratio by 3. And this is how you unbias for the streaming nature of the problem. And here are some results. So this is for a lot of graphs as well. We're looking at clustering coefficients. They're always close. And for a few of them, there is some difference. It's not as close as what we saw with wedge sampling, but this is a much harder problem. And in practice, we also looked at how much deviation we have, and it's always close by. So it's not like, these are not very hand-picked cases. You run it, and you'll get an accurate style most of the time. And the best part is that, well, for these experiments, we used only 20,000 edges for the edge pool and 20,000 wedges for the wedge pool. And for instance, Orkut has 200 million edges, and I can count the number of triangles just by using just kilobytes of memory. And there is extra benefit. Instead of 20,000, if you go to 30,000, it gets a little better. But after a while, it's just 40,000, just bring on the whole universe. I can count the triangles. So the graph can be as large as I want. Once you reach these 40,000 wedges, it's extremely memory efficient. And you can, for a stream, you can monitor these things in real time using a very limited memory. And just for an experiment, we did, this is for the citations graph. We did the same thing, and the analysis for the full enumeration versus, well, you see 2 runs here, counting number of triangles in real time and updating our data structures. And we can track these numbers in time. All right, so this is, I'll not get into details of this too much, but I talked about streaming, but whenever you have streaming, you also need to face off repeated edges. The streams don't come as unique edges, they come as repeated edges. And we always make the community assumption that before we start working on the graph, we remove all these repeated edges, we can do a lot of stuff, and then start applying algorithms. It's a fair assumption. It doesn't make too much time. I mean, well, if the problem is hard, just do that. Pre-process your data. But when you're working with a stream, you cannot do this. I mean, the edges keep coming, and you don't know if you've seen it before or not. So we extended the same idea for these multi-graphs, and the trick is using randomized hashing. Instead of flipping a random coin for each edge, I feed it to a randomized hash function. Once I set the seed for the hash function, each edge, no matter when I see it, will get mapped to the same hash value. And if I want to pick the first instance of one edge, I'll pick the last instance as well. So it doesn't make a difference. So that's good for detecting multiple edges. But there's also the problem with unbiasing. For instance, if I see AAA, BBBs, and CCC, this is smaller, corresponds to 1, 2, 3 edges example. Or it makes a difference if I see the same sequence as ABC, ABC. Because in the previous case, if I pick the wedge B and C, for the first sequence, I'll not be able to detect that it's closed. For the other sequence, I will detect that it's closed. And actually, that is a problem here because my unbiasing will not work anymore. So we have a technique for that. Instead of the future close, we're looking at lost future close. Instead of on the is closed variable, we sometimes reset the variable. Even if it detected as 1, return to 0 for certain cases. So I will not explain it here, but we can unbias it. And we have the version for, I think it should be on archive. Maybe it's on archive now, but if it's not, it will be soon, maybe tomorrow. So you can see the algorithm there. And we were able to analyze extreme large data set. And one thing nice was DBLD, we worked with the raw data. It's not sort of turning into a graph. We just looked at the raw data, the names of the authors, and then we analyzed the clustering coefficients for that. And we were extremely close in the analysis. And well, we generate some artificial data sets, and we always get good numbers as well. All right, so to conclude, so what I talked about was using sampling and streaming algorithms to analyze data. Especially, we were focused on just triadic measures on graphs, but most of the techniques will apply to higher data structures. We'll come back to that. And I started with talking about the algorithm, the first version of the algorithm that's on a single machine. And then while data gets bigger, while sampling, we always talk about larger data. And if your data is so large, how does it fit into a single processor, right? So we had a version for Hadoop implementation for the distributed case. And then in the last part, well, we extend this to the streaming case. I see the data once, and I cannot come back to it again. And well, in general, so you can see these papers are mostly they're online. But before that, I think sampling in general is a big part of a large-scale data analysis. Well, all of these data sets they're so large that we have to use sampling. We always talk about yes, data gets larger, and will have increased computational resources. But the increase in computational resources, I don't think they can keep up with the increase in data sizes. So we will need to use these sampling techniques as much as possible, at least to localize the data or detect something is abnormal. And error and confidence bounds, they're critical, especially if you want to, for practical problems, for real applications. Well, I don't know if you've thought about it, but you can literally offend people by proposing using sampling on their data. You can say, hey, we can use sampling to solve your problem efficiently. What? My data? You're sampling? You're not looking at half of my data? But if you give confidence, if you tell them, hey, I'll give you confidence bounds, and all the bounds, they're more eager to try your methods. And for John, here, I think this is for when we talk about graph kernels, how we do sampling on these graphs, how we use sampling kind of algorithms. I think that we should keep that in mind as well. And next steps, we start with triangles, but nothing. Why stop at triangles? We have to look at larger patterns, and to me, it's a two-way. So what can I count, and what's the implication? What does it tell me about the full graph? For triangles, we have an idea what it means. Well, if I look at these clustering coefficients and the degree distribution, I'll have an idea about the full graph. For larger patterns, I think we started to understand what they mean, and we are currently working on algorithms to count these things. It's not fiber-grained metrics, it's finer-grained metrics, it should be. And just a number of triangles or degree-based clustering coefficients, they're not sufficient, so we want to do more. And people already start asking questions. How about can you compute this and that? So we have to just do more finer-grained metrics in these graphs too. And one last thing is, for now, I'm looking at the whole the importance of the first edge and the last edge is the same. Well, that was by design. But at the same time, if you have time in your graph, that I sent an email 2 years ago to somebody, it's not the same thing as I sent an email 5 minutes ago. So we have to find something to evolve for these metrics, generalize the metrics for these analysis to include time. And some of the edges should age, and we need to define first nice models for to handle these things. And once we have these models, I think it will be much easier to generalize the algorithms for these new methods. With that, I'll stop and take your questions.